So for introduction to functions, what are we going to do here? So we are going to define what a relation is, what's the domain, what's the range, identify functions, use the vertical line test to identify functions, find the domain and range of functions, and get familiar with the function notation. Okay, so let's get an idea first before getting into the definition of a function that I'm pretty sure you've seen before. Let's consider that equation, y equals to 2x plus 1. So this is a relation that this equation describes relations between x values and y values. For example, if x equals to 1, then this equation describes how to find the y value related to x equals to 1. How come? Well, all we do is we compute y equals to 2 times quantity x, which is 1 plus 1, and then, well, 2 times 1 equals to 2 plus 1, that equals to 3. All right? So, I mean, and I'm pretty sure you're familiar with substituting values and plugging in for x and get those of y. Yes, that's essentially what we're going to do. But the real meaning, the deeper meaning is, well, that we have a relation between an input and an output, between an x and a y. So here, for the relationship here, or more formally relation, that's for the formal term in mathematics, between x and y defined by 2x plus 1, the x value of 1 is paired with the y value of 3. All right? So what we're really doing here, we're getting an order pair that we can graph on a Cartesian plane. All right? Now that we have an idea of what equations do in terms of what functions are, we can already look at, at a more generalized definition. So first of all, we will define what a relation is. So a relation is simply an order set of order pairs. That's all it is. All right. The domain, for which the domain is the relation of the relation, is a set of all first components of the order pairs. That is, so typically, check this out. Typically, all first components, that's the x component. All right, and the range of the relation is the set of all second components of the order pairs. That is the the y components. All right, bless you. Okay, so we're given a relation here. Let's forget about that y equals to x plus 1, which also happens to be a relation, by the way. Now, so we have this relation of order pairs. We have one order pair, 1, 2, 3, 4, 5, 6 order pairs. So in this case, they're asking us to find or to determine the domain and the range. So this is what we're going to do. I'm going to highlight all the x values with green. And all the y values with yellow. Let me use yellow. If you have colors, feel free to use them. If you prefer the use of other colors that work better for you, that's fine. All right? So this is what we're going to do here. They're asking us to list the domain. To state the domain, to write all the elements in the domain, we write another set of curly braces here. And we are going to list all the elements that I highlighted in green. All right? And preferably we write them in increasing order. Well, we see that the smallest of them is the -8 and then the -1. All right, so here is the thing. -8, comma, -1, comma, what's next? So 0, I think. And then what's next? Which one is the next one? 5. All right, do you notice that number 5 appears twice? Okay, you know, we only need to write it once, no need to write it twice. Actually, it's not correct to write it twice. And the reason I mentioned this, guys, is because when you're working on your MyMathLab homework, sometimes you are doing 15 minutes on a problem, you know, and you get the correct number, the correct answer. However, you input it on MyMathLab on the blank space, and you get it wrong and wrong and wrong. And well, when the third time you do that, I see it. I get it. It's so frustrating that you see the same result, but it only differs by a comma or some slightly different notation, right? So, and well, this is one of those cases in which Pearson is very picky with the input. So don't write elements in the domain or the range twice if they appear more, or thrice, or as many times as it shows. Just write it one time, and then there's the number 7. And I believe we're done with listing all the elements in the domain. All right. What else? Okay, let's write down the elements in the range. So that'll be, okay, 2, 3, 4, 5, or let's start with a 0, comma, the next one is the number 2, right? However, do you notice that the number 2 appears twice? So just write it once again. Then it comes the number 3, 4, and the number 4, and the number 5. All right? And that's how we list the elements in the domain and then the elements in the range. All right? Let's see what's next, by the way. Let's see. So, are we all done copying here? All right. Okay, now let's look at functions. So what we did is just a relation in general. So pretty much every single set of order pairs, or every equation, or every graph, or any mapping of ideas from domain to range, or domain to codomain, different ways to call it, is a relation. However, a function is a special relation in which the first component in the order pairs corresponds to only exactly one element in the second component. For example, well, let's look at some examples. So, let's determine the domain and the range of the following sets, and also they're asking us to state whether this relation, because again, these two are relations, so they're asking us to determine whether they are functions or not. And I'm going to use the bubble notation. You'll see what I'm talking about. So you can have a better visual of domain and between domain and range. So here is the thing. Okay, 1, 2, 1, 3, 4, 5. Well, good. They're in order. So that's 1, 3. I'm going to write them vertically. 1, 3, 4, and 5. And then I'm going to put them inside this ellipse, this oval here, and then I'm going to call this the domain. Call it just D. That's D for short. That's fine. And then let me write the elements that lie on the range. That is 3, 4, 5, 7. Good. They're in order. Great. 3, 4, 5, 7. All right. Let me make more space in between. Alrighty. So here's what we're going to do. I'm going to use arrows here to explicitly show the correspondence of every value in the domain to that in the range. For example, the first order pair is showing us a correspondence between x equals to 1 and y equals to 3. That is the element of 1 that lies in the domain, and 3, the one that lies in the range. The second order pair explicitly tells us that 3 gets paired with the number 4. The third order pair tells us that 4 is paired with the number 5, and last but not least, 5 gets paired with the number 7. All right? And this is, again, this bubble corresponds for the range. And that's fine. You can just use D and R for short. No worries. right? On a quiz or an exam or something, I would understand that that's domain or range. Now the question here is, does that relation represent a function?
Yes.
That is correct. Why so? Why is that a function though?
Because you can graph them.
Well, we can graph it even if it were not a function, all right?
It's because they're in order.
Even if they're-
in order at all.
And they're only used once.
Yeah.
And yes, they're used once. What about that once?
Because they all have like, they all correspond to one root.
Exactly. Every element in the domain corresponds to at most one in the range. Let's have a look at another example and see how the story can change in here. All right. So let's write the numbers 2, 3, 3, 4. Oh, we see a repeat here, right? So 2, 3. I'm not going to write the 3 twice. You'll see what I'm going to do here. And then 3, 4, 5, 7. Okay, 3, 4, 5, 7. All right. So let's use arrows again. So that's the domain, that's the range. And let's use, okay, the 2 is paired with the number 3. The second order pair is telling us that we paired the number 3 with the number 4. The third order pair is telling us that the number 3 gets paired with the number 5. And lastly, the number 4 gets paired with the number 7 here, all right? Now, I think when we look at just a set of order pairs, it's not so easy to determine whether this is a function or not. Of course, after some practice, you will get a better eye and you will be able to say by just looking at function, no, not a function. I think in this case, it's this double bubble here what help us determine whether we have a function or not. So what do you think about this one? Function or not a function?
Not a function.
Why not?
3 corresponds to 4 and 5.
Yes, 3 corresponds with your hint here. So here is the thing. The number 3 is going to two different values. I mean, think of the following real life example. Is it possible to be at 3 p.m. To be in class and at the beach at the same time? We wish it were possible, right? But it's not possible yet, right? Who knows, maybe in the future we can somehow split ourselves. I don't know. But I mean, coming back to the example for functions, well, that's a good way to explain why it's not a function. So you cannot be in two places at the same time. All right? So there is another example that I don't have here. I'm going to have it on the other one, on the other handout when we get there later. All right, so let's see. Example number 3. Okay, so this time around we're given the set of bubbles here. So, and it doesn't matter. They don't have to be in numbers all the time. We can have letters or ideas paired to a number, or a number paired to an idea, or a letter paired to a name of a city, or a number paired to a name of the month or the day. Well, but this is about correspondence here. So by looking at these couple of bubbles here, what would you say? Function or not a function?
Not a function.
Not a function. It's this A messing things up, right? This A is messing it up. It's A trying to be in two different places at the same time, right? Now here is the thing. Suppose we didn't have the following. Let me let me see if I have. Let me do all white here. All right. What if I didn't have? What if I have this instead? What if I didn't have this second arrow right there? So let's pretend we don't have that, right? Will that be a function?
Yeah. Yes.
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 Even go to D will go to 2, like arrow from D will go to 2. So
Exactly. So if we compare this to real life example, well, definitely we cannot be in two different places at the same time. But can we be in the same place at two different times?
No.
Yes.
Yes, you can come here in the morning to take Math 119, statistics, and then come at 12:45 to take trigonometry. It's possible to be in the same place at two different times, or maybe an English class, or I don't know. Actually, well, like coming to college, you are in the same place, in the same college at different times. So that's what this pairing represents. You know, at 9 a.m. I am in the third floor. At 12 p.m. I'm also in the third floor. All right. Okay, let's keep going. Let's see what about next one. Okay, determine whether each equation represents a function. Question.
Go back to that.
Sure. This one?
Yeah, so for it says you're gonna find the domain and range.
Oh yes, we didn't write the domain and well, actually it's right here, right? Domain.
Yeah.
Yeah, thank you. So, domain D and range R, either in curly braces or in the bubble notation. Either way is fine,
Okay.
depending on what's requested.
Yeah, so we make it into a function, like we just skip over the two.
Exactly. Yes. However, well, let me go back to the original. So originally it was not a function. The one I erased the second arrow just as a what if. All right, example number 4. So what about determining whether a given equation represents a function? How do we go about it? There's a bunch of ways to do it. Number one is by graphing, but let's pretend we don't know how to graph. All right? Let's use our knowledge. Well, here we're going to put a couple of techniques together because it turns out that it's going to be different for every single kind of equation. So, for example, y equals 3x plus 2. Okay, here's what I'm going to do. I'm going to generate a table of values. And I would like, we don't have to generate 5 values, 17 values, 59 values. No, just 2 or 3 is more than enough to notice a pattern and pick your favorite values of x. Well, in this case, one thing to notice is this is an explicit relation. What is that? What does it mean to have an explicit expression? Explicit, that's because since it is explicitly solved for y. All right? We have the y on the left-hand side. So one way to determine that the given equation represents a function is if we can see it explicitly solved for y, you can already say yes. All right? You can already say yes. However, if you're not convinced of this, and I'm pretty sure you're like, wait, why or how? Well, check this out. So let's see. So let's make a table of values. Not too many. Again, x and y. All right. So, for example, I'm going to start with 0, 1, and 2. I'm going to write 3 times 0 plus 2, 3 times 1 plus 2, and 3 times 2 plus 2. And simplify the results. Okay, 3 times 0 equals to 0 plus 2. Let me make this look like a 2. And that equals to 2. 3 times 1 equals to 3 plus 2, that equals to 5. 3 times 2 equals to, oh, hold on. Yeah, 3 times 2 is 6 plus 2, that equals to 8. So, what is it? 5 and 8. All right, this is more than enough for our purpose, for our next purpose. So again, do you see how we are relating x values with y values? So we can transfer these numbers, yes, into bubble notation. That is 0, 1, 2, these comprised elements in the domain, and 2, 5, 8, these 3 comprise elements in the range. And check this out. Do you see the correspondence here? 0 goes to 2, 1 goes to 5, 2 goes to 8 in this case. In other words, again, okay, another way rather to see this is for this relation y equals to 3x plus 2. If my input is 0, how many outputs do we have? Oh, I mean 2 is the result, but that's how many outputs? Only one output, right? So here we're only going to one single place at one single time. We're not getting two results for the same input, which in this case, yes, function. And using a little bit more formal language, that since every element in the domain corresponds to one single element in the range. That's the explanation behind. I know, again, after some practice, after looking at all these different kind of functions, you'll see how this will become a second nature, and you'll look at an expression. Oh yeah, function. Oh no, that's not a function. That one maybe let me do some work. Oh, function or not a function. You'll see. But in the meantime, what we're doing here is relating all the different ways to describe a relation that, in particular, actually behaves like a function. It is a function, but mostly the vocabulary and the definitions behind. All right, let's look at the second example, and I would like you to, yes.
That actually brings me up a question that I have for example 3.
Sure, let me go back to example number 3.
So say there was no a or 1 or 2, right? That's not a function. But with b and c both going to 3, that would be a function?
That would be a function because, for example, a going to 1 and 2 is again like trying to be in two different places at the same time. However, b and c going to the same output is being in two different places. No, being in the same place at two different times, like coming to this classroom at 9 p.m. and then coming later at 12 p.m. for another class. That's possible as opposed to being in two different places at the same time. Yes?
So B and C, we talking about a line.
Would be a line. Not a line. We're gonna get into those onto functions later. That's actually more behaving like a parabola. Different inputs getting the same output. Giving some sort of a symmetry, as we will discuss later. But that's good input here, right? Any other questions about? All right. Okay, I would like you to observe between A and B. How are the equations in letter A and B different to one another?
Well, b has an exponent. B has an exponent.
B has an exponent. Well, technically A has an exponent, invisible one, right? So, but yes, it's around that exponent. Let's go a little deeper into what is that meaning of that exponent, especially in the particular place it is at. All right? Yes.
It's explicit to x.
This one is explicit to x, all right? But the way we're going to describe this, okay, let me change color. So it's explicit for x, but not for y. But again, here we are going to focus on the y. So here, unfortunately, this is not an explicit relation, since it is not explicitly solve, whoops, for y, all right? As opposed to that's the difference between the two. Yes, I mean I see what you're saying. I mean we're looking at functions of x, but no, in this case we're still one. I mean for functions of y, we still want functions of x anyway. Okay, I'm going to reverse the order of this equation, and I purposely wrote it this way because this is most likely the way you may see it on the homework, right? So I'm going to write this as y squared. Y squared equals to x. Now, if we solve this equation for y, any ideas as to what to do to get the y by itself?
Square root.
Square root on both sides. Okay, let's see. Y then, so then y equals to the square root of x. So we take the square root, all right? We take the square root on both sides. These two cancel here, and that's going to leave us with radical x in the end, right? Do we all agree with this? Yes? I claim I'm missing something. What are any ideas as to what am I missing when I take the square root on both sides?
Square.
Not the square. Well, we got rid of the square already.
Oh, because they canceled each other.
Exactly. So yeah, this cancellation is fine. This radical is fine, but I left some space in here for something. That's my hint.
Plus minus.
The plus minus, right? That's in fact the square, how the square root property works. You know, when we solve a baby quadratic equation using the easiest method, which in this case is the square root property. Every time on an equation that we take the square root on both sides, we are supposed to have that plus or minus. Why is that? Because well, this is like a quadratic equation, isn't it? So potentially we should obtain two solutions for a quadratic equation. So that's one of the reasonings behind. There's another deeper having to do with absolute value equations and inequalities that, well, we're not going to get into that explanation. Now we have a relation, an equation that relates x's with y's, all right? And it looks sort of like the one we have in letter A. However, what do you notice weird about this very last result?
But there's still a square root.
It's still a square root. That's fine with the square root. That's fine. Well,
What, that there's gonna be two different answers?
exactly. How do we know it's going to be two different answers?
Plus minus.
The plus minus. So here, for if my input is, well, I would rather use, check this out. I'm gonna make another table of values. So x and y. All right. And well, I mean, you can plug in your favorite number if you want. However, think of numbers that have an exact square root, you know, like perfect squares, right? How about 4, 9, 25, all right? So the y values will be y equals plus or minus, what's that? Square root of 4, which is plus or minus 2, y equals to plus or minus square root of 9, which is plus or minus 3. And I mean, we don't have to go infinitely many numbers here. So in this case, plus or minus 25, I mean square root of 25, which is plus or minus 5. Now, how would the mapping for this would look like? Okay, what inputs do we have? Well, our only inputs are 4, 9, and 25. What about our outputs? In this case, we have a set of not only positive numbers, but also negative numbers, and I will write them from smaller to larger. So that is -5, -4, -2, +2, +4, and +5. All right. Those are the possible outcomes for at least for this table with the 3 inputs. And again, we don't have to do too many. I think from here we already got the answer, right?
-4.
Minus, okay, what happened here? 5, 3, right? 3, yeah, my bad. Thank you. Appreciate it. So this is what we're going to do. So, the number 4, in accordance with our table of values, the number 4 gets paired with -2 and also +2. Do you see how this number 4 is trying to be in the same place at 2 different times? That makes it not a function. The number 9 gets paired with -3 and 3. And lastly, the number, did you see the disaster this is becoming? I mean, even from the very beginning, we can already tell, no, not a function. However, I just wanted to show you how the map would look like to describe this relation, because, well, then we can call it a function. It's a relation. Later, in later courses, yes, you will call it a function, but a function of y, not a function of x. That's when you pretty much, no pun intended, you twist the plot and you define functions of y, where the inputs are y's and the outputs are x's. So, well, that's something you get to see in calculus when you describe different regions to find areas, volumes, and the like. Well, you'll see when you get there. Is there a shorter way to say not a function? Oh, yes, well, is it solved for y? Well, no. This is not solved for y, that's one way. However, we need to be careful, because when we solve it for y, we get the plus or minus. So the minute you see a plus or minus here, automatically say, no, that's not a function, because every input will generate 2 outputs. Now, there's a little downside here with y's not being solved for, with equations not being explicitly solved for x. And let me do that on the side. Check this out. So what if instead of x equals to y squared, I had x equals to y cubed? All right? So the way, okay, right now, well, initially that doesn't look like a function because y is not solved explicitly. All right? That's our first thought here. However, well, let's see if we can solve for y. So in the same way that we took the square root on both sides in letter B, what would we do to get the y by itself for the y cubed? Cube root. So first of all, y cubed, let me change the order, and then cube root. Whoops, y cubed equals to cube root of x, and y equals cube root of x. And by the way, guys, this cube root doesn't need the plus or minus in comparison with the square root. It turns out that when we use that root and root property, we only put the plus or minus only when we're dealing with even indices here, like if we're taking square root on both sides, if we're taking the 4th root on both sides, the 6th root, the 8th root, the 10th root, it's all even indices. However, when it comes to odd indices, like I think I missed a 3 here. I should have wrote a 3 here, yes. Like the cube root, the 5th root, the 7th root, the 9th root, etc. We don't use that plus minus. All right? And in this case, well, if we observe this equation for every single x, since we don't see any plus minus here, we're not going to get 2 outputs, so we can call this an actual function. And let's see. For letter C, I think we can already tell whether this function, this relation rather, is a function or not. What would you say about it? Not a function, right? How come? Well, it's this plus or minus messing it up. Two outputs for a single input. All right, two outputs for a single input. Therefore, not a function. All right. So let's look at the vertical line test, which is a way shorter way to determine whether we have a function or not. All right, so the definition goes like this: if no vertical line can be drawn so that it intersects a graph more than once, then we have the graph of a function. In other words, what we're going to do, trace a vertical line test, and if it crosses more than once, it's not a function. Otherwise, it is a function. So let's do this exercise. State whether the following graphs represent functions. Well, if I trace a vertical line test, well, it's crossing only once, or at most once, right? So it is a function in this case. It doesn't matter where you trace that vertical line test. Everywhere you trace it, it crosses at most once. So yes, right? What about the second example? Function or not a function? If we trace a vertical line test,
Function.
yeah, it is a function, right? Still a function. However, look at this sideways parabola.
No.
Not a function, right? Now, here's the thing. You might argue that at the very vertex of this parabola, well, we can trace it and it crosses only once. Well, that's true, I agree. However, for the remaining sector of the graph, or the part of the graph, every single vertical line it crosses more than once. So, yes, no. And well, what about this ellipse? That's not a function either, right? No. And again, you might argue that on the edges here it crosses only one, but yet we have all the other points in between for which a vertical line crosses more than once. All right. Finding the value of a function. So we are going to be given a few equations now. What's the difference? I mean, 3x minus 5, 3x squared minus 4x minus 5, 7x squared minus 3. I mean, that doesn't look any different from what we have worked before, other than the notation. I mean, coming back to what we got over here, we always got y equals something, y equals something, y equals something. Here, we're going to introduce this function notation to number one, distinguish between one function and another one. Because in the previous examples, when we say y, well, it could refer to the same function actually. All right. So in this case, when we see this notation f parentheses x, careful, that doesn't mean multiplication. That means f of x, right? Okay, so that means f of x, or f evaluated at x. All right, f of x or f evaluated at x. However, we use the shorter version. We don't use the longer f evaluated. It is understood that we will evaluate the function, right? So just f of x, it's more than enough. Same here. Let me use a different color. G of x. That's how we read this. And let's call this h of x. All right? F of x, g of x, and h of x. Those are, by the way, the most common letters to label functions: f, g, and h. Of course, other Other letters come into play, well, depending on the situation. For example, in a pre-calculus course or in college algebra, when you look at rational functions, typically over there they use uppercase letters like big F, big G, big H, also big R to represent, to call it R for rational. Well, you'll get into those later. Now, here is the thing. We have a couple of instructions here. G parentheses 3, S parentheses -4, H parentheses -1. So here, this is what the instruction means. This means evaluate the function G at x equals to 3. That is, let me highlight the function G. By the way, I use the same color to color code so you can see where am I inputting and what. All right, let me highlight this G function with green. Let's see, so this is what we're going to do. We're going to evaluate so 3. Okay, I'm going to leave parentheses for now. In other words, here what we have to do is that everywhere you see the letter X in your function, substitute. All right? Substitute the number 3 right here. So 3 times parentheses squared minus 4 times parentheses minus 5. Well, so in this case we want to evaluate it for 3. All right? And that's a 3, all right? And just follow the order of operations in accordance with pandas, right? Well, here what do we have? Parentheses, exponents, we do the exponents for, well, yes, there's parentheses, but everything inside of the parentheses is already simplified. It's just the number 3, square that, and then multiply by 3. So 3 squared, which happens to be 9, times 3, 9 times 3 equals to 27, and minus 4 times 3, which is 12, and then minus 5, and then just combine the numbers. So 27 minus 12, so that's 25, that's 15, and then 15 minus 5, that's a 10. All right. And again, if just to briefly keep going back and forth between these definitions of functions and relations. So again, this function G relates x values with y values in accordance with the rule 3x squared minus 4x minus 5. All right. So let's see. The next one, f of -4, they're asking us to now go with the function f. Be careful, I label them. I color code them, not label, not necessarily label. So this is our function f, 3x minus 5. And again, well, I'm not going to write this anymore. I think one example is fine. So what we're going to do is replace every instance of x, and by the way, there's only one, replace it with the number -4 and simplify. So that is 3 times -4 minus 5. And well, let's just simplify this. We do the multiplication first and then the subtraction. 3 times -4, is that -12? And then minus 5. Careful, because we're adding 2 negatives essentially. Careful with that one. So I am losing 12 and then I lose another 5. So I lost a total of 17. That is -17. All right. And well, last example with a function h, which I'll highlight with yellow, right? And so simply, so that's 7 times quantity squared minus 3, put a -1. Okay, let's simplify this. So -1 quantity squared, what's the result of squaring a negative number? Careful.
1.
Positive, it becomes positive, right? So negative square is positive. 1 times 7, that's a 7 minus 3, and that equals to 4. I mean, that doesn't look any different from something we did at the beginning, like plugging in values of x to obtain values of y, except that this time we're using the function notation instead of just y equals expression, y equals expression. And in many cases, it will matter the choice of f, g, and h. All right? Okay. Let me pause the recording for a second. These ones together. Okay. So again, so we are given some random function that we don't know. That function, of course, is going to generate a bunch of points, a huge relation of points that relate x's with y's. All right. And one of those particular points is f of 3 equals to 9. So letter A, when x equals to 3, y equals to 9. True or false? True. All right? And that's because essentially this is x and this value equals to y. Again, we are replacing the y letter in an equation for a more formal symbol, call it f, g, h, etc. A possible function that generates that order pair is f of x equals to x squared. True or false?
For sure.
True. All right? And that's because if we evaluate f of 3, that's equals, 3 squared, that equals to 9. Which means f of 3 equals to 9, which corresponds to what we're given, right?
So for A, the x there's the invisible exponent or something.
Exactly. The x is the quantity inside of the parentheses, and whatever is on the other side by itself as a number of the equal, that's the y value.
Isn't the invisible exponent though 1, not 2?
Yes. So there's a. Do you mean here?
Yeah, with f of 3 equals to 9.
Mm-hmm.
Like how does that become 9? I get it that 3 times 3 is 9.
Oh no, that's just a random function value given without even knowing what the function is. And well, in this case, what we're discussing is whether in letter B, whether a potential function is indeed x squared, and it turns out it's true because when we square this number 3, we obtain the number 9. And well, letter C, a point on the graph of the function is the point.
Okay. I see. I was looking at
Oh, okay, that's fine.
evaluating it instead of the actual.
Oh yeah, no, in this case I see where the weirdness goes, because no, we're not given an explicit function yet. It's just suppose some random functions and we can generate other functions, right? So, okay, a point on the graph of the function is the order pair 3, 9. True or false? I mean, this is just another way to say x equals to 3, y equals to 9, right? X equals to 3 and y equals to 9. All right? Letter D, a possible function is f of x equals to 2x plus 4. True or false? False. All right? Okay. What would be a good function? Okay, how can you fix instead this function? So instead of having the square function, but using the linear function, still outputs the point 3, 9. Yes?
You need to change the 4 to a 3.
Exactly, right? But h of x equal, or g of x, it doesn't matter, equals to 2x plus 3. That one is. All right? And let's see, I believe this is the end of this handout, right?